In example 111, we've got another compound interest situation. This time, we're trying to solve for t. How long will it take $10,000 to grow to $12,000? We have an interest rate of 9%, compounded monthly. So here are the players in our compound interest formula. This time it's the value for time that we don't know. It's compounded monthly, so M is 12. The interest rate is 9%, 0.09. The principal is $10,000, and we want to end up with $12,000. And so I'm going to start off, just like I usually do, by writing down the formula for compound interest. And we're trying to solve for t. So the first thing we could, might observe here is our goal, solving for t. T is trapped up there as an exponent on this set of parentheses on the expression below. And so we know that when we're solving for a value that is trapped up as an exponent on some base, logs are going to be involved somewhere. So let's throw in the values that we know here and see how far we can get and where logs come into play. So A is 12,000, P is 10,000, then in the parentheses 1 plus 0.09 over 12, and M is 12, so our exponent is 12t. I'm going to simplify that expression in the parentheses. 0.09 divided by 12 is 0.0075, so plus 1 gives us 1.0075, all to the 12t. Now we know that logs are going to be involved in order to help us pull that exponent down, but we're not ready to do that until we get rid of this factor that we have out in front. So we're going to divide both sides by 10,000. On the left side, that ends up with giving us 1.2. On the right side now, we have 1.0075 to the 12t. Now that I have this expressed as just some, a base, 1.0075 raised to this power, and no other factors or terms added on, we're ready to use logs to help us solve for t. So I'm going to take the natural log of both sides. Now remember, you could pick either the natural log or the common log. It really doesn't matter. But I'm going to take the natural log of both sides. And when we do that, we are allowed to, and the reason that we're doing it is because it allows us to bring that 12t exponent down in front as a factor in front of the ln. So we have ln of 1.2 is equal to 12t times ln of 1.0075. Now at this point, we know that we're looking for t, we're solving for t. However, what I'm going to focus on here is actually first solving for 12t. And this is going to be the approach we want to take whenever we're looking for the amount of time in one of these compound interest periods. Figure out how many compounding periods. In a compound interest situation, your lengths, your intervals of time only exist in steps of those compounding periods. So since these accounts are in compounded monthly, then time only exists in months. And for all practical purposes here, there's nothing that exists between, say, 6 months and 7 months. You're at the 6 months, there's no 6.5 months. So we're going to solve for 12t first to get the number of months, and then we can interpret that result and say how many years and months from there. So in order to do that, we're going to divide both sides by the natural log of 1.0075. And so this will give us 12t is equal to this fraction, which we can compute on our calculators. So natural log 1.2, close your parentheses, divide, natural log 1.0075. We get 24.4. Four, 401. It doesn't really matter because all we know is it's 24 and change. And since time only exists in increments of a month at a time, what this tells us is rounding down 24 months is not quite enough. That's not going to get us quite to the 12,000. In order to ensure that we reach our goal, we have to round this up. So when you're solving for a time and the number of compounding periods, always round this figure up. So we need 25 months, or 2 years and 1 month.